Okay, so let's move forward. The intrinsic diffusivity, which observed in crystal frame. The material system, as we mentioned in the intrinsic diffusivity, actually is we have a concentration variation in our material system. So let's take this as an example. If we have a diffusion couple, component 1, 2, and based on the concentration profile, you know that there's inhomogeneous, chemically inhomogeneous medium. And as we mentioned before, if we stand on at the interface, which means we stay in the crystal frame. And in this case, the diffusivity we measure or observe is belongs to the intrinsic diffusivity. And as we mentioned, that's a very important constraint we call a network constraint. If you divide it by the time period and also the area, so you can get the other form of the network constraint is the summation, the summation of total flux equals to 0, or some people call it as a net flux. Net flux inside this material at any specific plane equals to 0. Okay, so as we mentioned, there's two important information or you need to learn from this diffusion couple, right? Based on if J1 larger than J2, the first of all, in order to reach the net flux equals to 0, there are definitely a vacancy flux toward to left-handed side. So which means, and also due to J1 larger than J2, so the interface definitely moved to the left-handed side, so the junction moves in the opposite direction of the flux with a faster diffusion component. Okay, and after series deviation shown in page 15 in lecture note, the results demonstrate that intrinsic diffusivity can express like this, and you can simply divide it into two terms, first term and the second term. The first term actually, I believe you're familiar with this one, right? It's a little bit similar with what you learned from previous slide. You learn in self-diffusivity. Just substitute the star 1 with 2, right? It's identical, actually it's the same. So the first term actually is a self-diffusivity. We just the different parts we just change the star 1 by 2. And the second term actually is very interesting. If you take carefully, what you find here is we got the gamma, log gamma partial with the log concentration, and also the log omega partial with the log concentration. So what's the gamma? Actually, in thermodynamics, you learn that gamma is the activity coefficient. So as you learn here, is we know the thermodynamic activity A equals to gamma times the atomic fraction. And also gamma can be expressed like a concentration times the average atomic volume. So you can get this relationship, right? And I'm going to give you some review on the gamma. When we talk about the gamma in thermodynamics, actually, in that part, actually, we talk about the mixture between material A and B. It belongs to ideal mixture, ideal solution, or non-ideal solution or non-ideal mixture. So in that part, we learn there's two important laws, which are Henry's law and Raoult's law. Raoult's law actually is an ideal solution, and Henry's law actually is a non-ideal solution. So in that part, actually, the A equals to the vapor pressure after mixture divided by the vapor pressure before mixture equals to gamma times the atomic fraction. And you know gamma actually is a function of temperature and composition. And gamma equals to 1. What means gamma equals to 1? When you plot the A versus the X, the gamma equals to 1 actually is obey this dashed line, right? This gamma equals to 1 means the A equals to X. In this case, actually, we call it is a ideal solution. Okay, and if your mixture is not belongs to ideal solution, can be non-ideal solution. And non-ideal solution, there are two possible ways. The first one is the gamma larger than 1 or gamma smaller than 1. So this purple curve actually is deviated. Gamma larger than 1 is positive deviated from Raoult's law. It's one kind of non-ideal solution. If gamma larger than 1 tell you what? The vapor pressure after mixture is larger than before mixture. After mixture means the AB contraction, you have a higher vapor pressure, means the after mixture the AB attraction is stronger. Oh, sorry, is smaller, is weaker than before mixture, means the AB and BB, right? Because it's the bond energy is weaker, so you got the higher vapor pressure. And because the attraction of bond energy actually is weaker, so and also you know the bond energy belongs to negative, so AA and BB is stronger, right? So it's more negative. So more negative 1 will decrease the total free energy of a system. So these solutions or these mixtures will go to phase separate because phase separate can lead the minimum gives free energy. If the gamma is smaller than 1, means the negative deviated from the Raoult's law, then in this case the vapor pressure after mixture is what? Because this is negative, this is smaller than 1, so this will be smaller, right? Smaller means after mixture, AB's attraction or bond strength is stronger, right? So that will lead the lower vapor pressure after mixture. In this case, stronger, so bond energy also negative, so more negative will lead the minima free energy of a system. So this material system will tend to be a compound material. So this is a quick review about the gamma. Okay, so let's back to here. So the intrinsic diffusivity related to the second term will be related to gamma partial with log C concentration, and also plus this term, right? And this term actually is the average atomic volume. It's nothing related with the concentration, right? So you can directly delete this term. And we also make a very important assumption. We assume the coupling coefficient is very small, included this term and this term is very small compared to the direct effect. So we can delete this term. So we can simplify this intrinsic diffusivity as expressed like this. Intrinsic diffusivity, and this term actually is a self-diffusivity, right? And times this term, because only delete this term, so you only have these two terms. So you know that intrinsic diffusivity is proportional with self-diffusivity and also a concentration-dependent part. and also related with this materials, this mixture or this materials is belongs to ideal or non-ideal solution. And if you also want to further simplify this, you can make additional assumption. If this is ideal solution, then gamma equals to 1 is nothing related with concentration, so you can directly delete this term out. So you got the intrinsic diffusivity equals to self-diffusivity when it is ideal solution or dilute solution. Dilute solution, right? Okay, so let's move forward. So let's move to the last part is interdiffusivity, which is the diffusivity when you measure the diffusivity in the lab outside the materials, and also the material system belongs to chemically inhomogeneous medium. Here we parallel show the intrinsic diffusivity and interdiffusivity. And for the intrinsic diffusivity, which means when the observator stand inside at this interface, then when he measure how many atoms, atom 1 and atom 2 passing through this interface, then he will get this, right, will obey fixed first law. But however, if the observator stand outside this material when he want to explain or calculate, measure how many atoms passing through this interface, due to this interface moving, that means the coordinate, a reference coordinate moving, so you can find that there's more atoms passing or crossing across this interface because the atoms, this interface moving. So J1 prime, the real mass flux measured by the observator stand outside the materials equals to J1 is belongs to fixed first law part, and C1V is a modified term which due to the interface movement. So it's C1V, so you need to end this extra term. This extra term actually due to the interface moved from this here to here, so there's more atoms. These atoms should actually did passing through this interface, right? Okay, so finally you got this relationship, and so we got the flux be modified flux for flux 1 and flux 2, and we use this relationship, then we can derive the J1 prime and J2 prime. So what's this relationship? People call it as a volume fix or lab friend. Means what this means actually is when diffusion happens, the total volume move from the right-handed side will equal to the total volume move to the left-handed side. So during diffusion, we don't have chance to observe our samples moving, right? It always stay there, right? When you put on the stage, your all samples always stay there. So that implies that even interdiffusion happens, so the total volume, the total volume change, no matters for atom 1 or atom 2 will equals to 0. So based on this relationship, we can derive the J1 prime expressed like this. So the interdiffusivity actually here will be D1x2 plus D2x1 is the concentration dependent diffusivity for sure. And J2 prime also is a minus D hat concentration gradient. So here I just a quick remind for interdiffusivity, which we always deal with, we only have one diffusivity, and this diffusivity is concentration dependent diffusivity. And in order to simplify the question or the problem we deal with, we assume if x1 is very small, means the x2 approach near almost equals to 1. In this case, we got the this term, this delete this term, and this equals to d1, right? So the interdiffusivity will be equals to intrinsic diffusivity. And also in previous slide, we showed that ideal solution, the intrinsic diffusivity will equals to self-diffusivity. So we make a summary here. So if your material system belongs to ideal solution or dilute solution, the self-diffusivity equals to intrinsic diffusivity will equal to interdiffusivity. All these diffusivity are the same. So back to the opening for this part. Why in the questions you calculate for diffusion, they didn't mention what types of diffusivity they provide to you, because in most of cases they assume the system, the material system we deal with belongs to ideal solution or dilute solution. It's only lightly doped or lightly one interdiffusion only very small tiny amount of one dope or diffuse into component 2. So we call it dilute solution, right? Okay, so today we just ended here.